All right, hello and welcome to the next set of lectures. This set of slides is like a potpourri of topics, and I have titled it Fancy C++. So let's go with that. The very first thing that I want to talk about with you is some information about the final and some new extra credit. So let's go there. Over here in one of my many tabs. So down here, I'm going to eventually make this week 18 module available, and it will have the final exam in it eventually. But right now it has final info and then the extra credit assignment. So let's look at those. So the final is going to be a 2-hour exam, and I'm going to make it available the day that I said back at the start of the semester. It's going to be available starting on the Tuesday of finals week. So December 8th is a Tuesday, and it will be available until the Wednesday. So a little over 24 hours to take it. Okay, so you can start anytime. It's a 2-hour exam, so make sure you start it before 12 on the 9th if you start it on that day. Really, for this college, final exams are supposed to be 1 hour and 50 minutes, so I'm going to make an 1 hour and 50-minute exam, but I'll just give you 10 extra minutes to take it. How about that? Okay, it is cumulative. Everything in this class builds on top of itself anyway, so there's no real getting around that. But here is a list of the topics that you should definitely be familiar with and ready for. So all topics from the first 2 midterms, of course, and then stuff from after, things that were due after the midterm. Okay, so all this stuff. I will try and give a few more questions on the later things, but I can't make any promises, so just expect stuff from everything. For topics that are after Huffman compression, after last week's topics, like this one, for this week, you should still expect to see some questions, but they won't be a lot of weight or many points if they appear at all, because some of this stuff is just meant to get you ready for the next class, and it's not something I want to teach you on, not something I want to test you on right now. So yeah, there will be multiple choice questions again from the remaining chapters, but keep in mind that there are not a lot of remaining chapters for these topics. And then there will also be some fill-in-the-blank and coding questions taken from all the topics. So just get ready to paste code in a text box as usual. One thing that I do want to talk about are some of the sections of the book that I'm not going to test you on. I'm making you read, but I'm not asking you that I'm not going to test you on. So that would be sets a little bit. I've talked about the map data structure. That's about all that you need to care about, and maybe unordered map. Sets I won't really be testing you on. Graphs I will definitely not be testing you on. Balanced trees I will not be testing you on. Okay? Because those are things I didn't even go over in lecture. If I didn't go over it in lecture, then it is not going to be on the exam. Okay? That's the idea. So that's that. And then extra credit. Something that is due the final day of instruction, so December 4th. Go ahead and make a review video. A review video, this will be up to 5% extra credit, so use it if you need it. And just make sure to turn it on time. So just like last time, please make a video that reviews concepts that will appear on the final and post it so your peers can see it and you can help them study, and they will love you forever, of course. So yeah, just make a bunch of examples for topics that you might be tested on. Don't make them super easy, and you should cover things that will appear on the final, but just don't copy one of my lectures, okay? So don't make it unlike something that's in class, and don't redo like an assignment. Be creative, make it brand new. And if you have any issues recording yourself, please let me know. I can give you an alternative extra credit assignment. We'll make it work for you. I can help you get a laptop from the school even, if need be, okay? So I want you to be able to do this extra credit. If you have anything that's stopping you from doing it, that is not something that you can control, we will help get you extra credit, all right, if you want to do this. So yeah, if you want the full 5%, you got to make a 40-minute video, okay? That's a bit long, but trust me, it's not too bad. I've been doing it for a while now. 2.5% extra credit is 20 minutes, at least 20 minutes of a video, and then 1.25% extra credit for a 10-minute video. So maybe a quick example for a little bit of extra credit. So consider doing it, and that's all I have to say there. I'll go back to here, and that's where I want to start. So let's get started. First, we will make our own exceptions, and it might have been a while since you've used exceptions. This is more of a 40 concept that I didn't really hit very hard in this class, but it's like you try to do something, and then that thing that you do may have thrown an exception, so you catch it. Like maybe it's a runtime error. You usually catch it by reference, and then once you've caught it, like there's a brace here, then you handle it. Handle E ... And that is exceptions in a nutshell, in case you forgot. Now, let's make our own, because what is an exception but a subclass of standard exception? Like runtime error, for example, it's a subclass of exception. What? So if I go here to runtime error, which exists in standard except, oh man, a runtime error is an exception. So we can make our own version of exception. We can do it just like this, okay? And what we can do is, well, in order to make an exception, we just have to override certain methods, okay? We'll override this method that doesn't exist right now, the what method that returns a C string saying what went wrong, okay? So let's do that. Let's make our own custom subclass of exceptions. And so we've checked and seen now what's inside of an exception. It's just that one what. Like, you got an exception, you have to call what on it. That gives back like what error actually happened. And really, technically, you don't have to subclass exception, but it's good practice to do so in real-world C++ programming. But you can just, like, if you wanted to, you could throw the number 42. That's an exception. Totally valid to throw an int, any type that you wanted to throw. But let's make a subclass of exception and make our own version of an exception. Okay. Boop. Is this the right thing? I think it is. So vim exceptions.cpp. So we need standard except. We need, I'm going to use strings, and so public my exception, because I'm about to throw it, right? No, sorry. I'm thinking of Java. Class my exception, public exception. So it's a subclass of the exception class. And eventually we're going to use it. We'll be like, if 42 is less than 43, throw my exception. I don't know, 42 is less than 43 or something. We'll just make our own version of exception, and we can catch it. Catch a my exception by reference. And then normally when you get an exception, you like output what went wrong, you say e.what. And we'll have a what because we are a subclass of exception, so we're going to implement that. All right, so let's have, I don't know, public, private. The private thing could be like a string description that has information about what went wrong. That's like essentially what we did here. And so we'll have like a constructor that's like, okay, a my exception, when you give it a string, we will use that string to set the description. Description equals like, oh no, something horrible happened. This is our custom exception. We can say whatever we want. Let me say plus s or something. That's our description of our exception. And then all we have to do to make this an exception, remember, is to override this what operation. So we say const char star what const, and then obviously if this is an exception and got thrown, trying to figure out what happened inside the exception should not itself throw an exception. That would be horrible. So what is a no except kind of function. And it returns, this is a C string. It's a constant C string. Char star is a C string. And this is an override, so we can say that. And we can return something. We eventually want to return description, but we want to return it as a C string. So what do you know? The string class, any object of the string class's type, has a .cstring method that turns it into, oh man, a constant char star. Beautiful. Bam. We got it. All right. So, no, sorry, I want to try doing all this and then catch if necessary. Usually those are on the same line. How about that? There we go. So in theory, we have just made our own exception class, overrode the what operation to say what happened when we threw an exception, and then we printed out what went wrong. Okay, let's be like g++. Boop. And something horrible happened, 42 is less than 43. And because this is an exception, it's of the exception class's type. C++ knows how to handle it when it just is not handled properly. So let me do this. Let me just throw my exception without catching it. And you know what happens when that happens. It terminates the program, but because it's an exception, it knows that it's an exception. It knows that it can call the what. Yeah? So it'll print out our what for us, which is super nice because you'll usually want to know that. So that's why you want a subclass exception, because if you forget to catch it, you get some nice features. That's one reason, at least. So that is a custom exception. We made our own. We rolled our own. All right. So that's one thing. This is like a lot of topics. There's a potpourri of topics. The next one is bitwise operations. And so we are doing operations on the bits of a number. So we've got like 0, 1, 0, 1. Like we are like extracting the 0. Hey, that's a 0. Or we can like set this one to a 1. Set, extract. Things like that. Bitwise operations. So you might have heard about this in 40, but I want to make sure that you've heard about them before you take CSCI 45, no matter what. So let's remember how numbers work. If you have an int or an unsigned int, those take up 32 bits of space. So you've got 32 ones and zeros. All right, 32 of them. 32 ones or zeros to make up an int or an unsigned int. And an unsigned int is just an int, but it can't hold negative values. So it has a bit more extra space to hold like larger numbers. Ints, though, ints by themselves, they take up 32 bits, but they can also hold negative numbers. How in the world does a computer store a negative number, you might ask? So let's figure out what -1 needs to be. We know what it should do if we add it. Okay, so let me start with, let's pretend we have 8-bit numbers, so they all have 8 bits only. That's as much as you can hold. Let's figure out what -1 should be by adding it to 1. We know that we need to get back 0, right? So how in the world can we take 1? We need to find out what -1 should be. Now we need to get back 0. So the trick is, okay, what needs to go here? This is the first digit you add, right? So it cannot be a 0 because that would force this to be a 1. We need it to be a 0, which means our only other option is this is a 1 and this now has a carry. Okay, so this is 1 plus 1, it's 2, 1, 0 in binary. So this makes that a 0. And now we have the same problem. We have 1. We can't put a 0 here because that would make this a 1. We want it to be a 0 because we want the final result to be 0. Okay, so again, we now have to put a 1. And you have to follow this all over the place. Carry, add a 1, carry, add a 1, carry, add a 1. On and on and on until the end of time. And this, in fact, is -1. It's all 1s. In binary, in 8-bit binary, 8 1s is -1. Because when you add, you get 0 back. Because this final carry, you drop it. Because there's not enough space. This is an 8-bit number, I said. There's no 9th bit. Yeah? That's the idea. Or technically, this is the 0th bit, so there's no 8th bit. So the reason this works is because we throw away that final carry bit, and you can come up with this for every number. Like you could play the same game with like 2 and things, but let me just show you the trick. You do what's called 2's complement, which first you flip all the bits and then you add 1. Okay? So that's how you convert any number into its negative form. So start at 0, or start at 1. Sorry. Then you flip the bits. So all the zeros become 1s and vice versa. 1, 1, 1, 1, 1, 1, 1, 0. And then you add 1. And that'll just change this one, right? And so it's 1, 1, 1, 1, 1, 1, 1, 1. Yeah, so that's -1. And you can do it in reverse as well. You can do it in reverse, and it goes right back. So if you have -1, you can flip the bits. Oops. Flip the bits, which is all zeros. And then you can add 1, and then you get back 1. And so that's how you can negate in both ways. Okay? And you can do this for 2. I encourage you to try it. This 2's complement form works perfectly. The flipping all the bits is called 1's complement, but we want 2's complement, so we add 1. And that converts it to a negative number, and it follows all the patterns that you expect. So that is how numbers are arranged in memory, in case you were never taught that or you forgot. So with that, we can now talk about these bitwise operations. I don't want to spend a ton of time on it, but so I've put a bunch of, like a wall of text on this slide, I'm sorry. But we'll go through it. So a bitwise operation, it allows you to do non-number stuff to a number, if that makes any sense at all. And the idea is, okay, here's my number. I will use the first bit to store whether or not, like, the game is currently running. Like, I'm not in the title screen. Game is going. I'll use the 5th bit, 0, 1, 2, 3, sorry, the 4th bit to determine whether or not I have, like, the special health pack from the game. And I'll use 5, 6, the 7th, the 8th bit to determine whether or not I don't know, I have an extra life. So numbers are a really compact way of storing Booleans. You can store 32 true and false values very compactly in an int and manipulate them separately. Okay? So let's talk about the first bitwise operation. It's called bitwise and it uses the ampersand operator to do it. So you have a third thing that the ampersand can do, and I am so sorry. C++ is disgusting. I know. So what the ampersand operator does, it's a bitwise operator. It performs Boolean and on 2 numbers, and it works on each bit at a time. So it like lines them up and does and. So here are my 2 numbers: 1, 1, 0, 1, 0, 1, 1, 0, and 0, 1, 1, 1, 0, 0, 1, 1. And I AND these 2 together, if I can write an ampersand correctly. What it does is it lines up each number and looks at the bits of those 2 numbers in a line. And so it does the AND operation on both of them. Remember, 0 is false, 1's true. So false and true, well, that's still false, 0. True and true, hey, that's a 1, cool. True and false, well, they have to both be true for it to be true, so false, false, true, false, true, false. Yeah, that's the AND operation, the bitwise AND operation. And is useful for testing whether a bit is set. So notice that, hey, the second number, it had a 1 here, so if there was also a 1 here, I will set that bit. You see that? I can test whether or not it was a 1 by ANDing with a 1 in that position and seeing if it was a non-zero value. So let me show you this in code. It makes a bit more sense. So if I have int x equals 15, which this 15 is 1, 1, 1, 1 in binary, I can test and see if the third bit is set by ANDing with 8, which is 1, 0, 0, 0. You see that? It's just that 1 bit right there. So if I AND that with that, those 2 numbers together, this one with that one, I will get back 1, 0, 0, 0, which is not equal to, can I do, which is not equal to 0. Okay, that's useful. I can say, okay, 15, or sorry, x mod, I could have just put 15 as well, x mod 8, check and see if that's unequal to 0. Because if it is unequal to 0, that means the bit was set. Okay? A true value means the bit was set. I hope that makes sense. We got back a non-zero value because if it was 0, then this whole thing, the result of the AND operation, would have been 0. And so let's watch it work. And it was 1 for true. Yes, it was set. And I can also check, hey, was the bit after that set? Was bit 4 set? Because 16 is 1 and then 4 zeros. It's essentially doing this operation, 1, 1, 1, 1, and 1, 0, 0, 0. These don't align, so that's equal to 0. So the bit was not set. Okay? So it is equal to 0, it's false. That bit was not set. Cool, huh? So the rest of these probably make a whole lot of sense now. So bitwise OR, it's this pipe operator, and it just does the OR operation instead of the AND on these bits. Okay? Remember what OR does, just Boolean logical OR. And it's useful for setting a bit, because maybe I start with 0. If I OR by 8, then OR by 4, then OR by 2, then OR by 1, this is actually going to print 15. Because first we start out with 0, all zeros. Then I OR that with 8, which is 1, 0, 0, 0, 0. That gives me back 1, 0, 0, 0, 0, because it ORs this one. It ORs this bit, this 1 with this 0, and it produces 1, 0, 0, 0. Yeah? And so then we can do 4 after that. We have 1, 0, 0, 0, or with 4, which is 0, 1, 0, 0. And that gives us back 1, 1, 0, 0. On and on and on until we get back 1, 1, 1, 1. I hope that makes sense. So start with 0 and then just OR things, OR single bits at a time, and we'll get back 15. We'll set all the bits. Hey, we did it. So that is that in a nutshell. That's the OR operation. Bitwise NOT is this little tilde. It flips all the bits. So whatever was 0, 0, 0, like you NOT that, it becomes like all ones. It just flips all the bits. Like if that were a 1, this would be a 0. That's the idea. So we can negate now. We can use 2's complement ourselves. We can be like, all right, -1 is start with 1, flip all the bits, add 1. And the compiler will be like, okay, you wanted to print out a number, so I'm just going to make this look pretty for you. But it's really -1. It's all ones. Yeah? Isn't that fun? So that's exciting. XOR performs the exclusive OR operation on each bit, and you might have not heard of this. So XOR, if I have A and B, then I want to do A XOR B, this is what happens. This is the truth table. True, false, false, true, false, false. A XOR B, it's like OR, but it's called exclusive OR. So this is the truth table. False, true, true, true. So the one difference is right here. If they're both true, A XOR B is actually false. So this is true with OR. The regular OR, which is known as the inclusive OR. So XOR B, it's like exclusive OR, is what it's called, and it's like, okay, either one or the other is true, but not both, okay? That's what it means to be exclusive OR. And that's useful for flipping bits. So you can flip a bit with XOR. You can XOR with 1 in that position. So maybe like int y equals 15, y equals y, XOR 8 to get rid of that bit right now. So this will just be 7. Now it's just 1, 1, 1, 1. See out y. It's 1, 1, 1, 1 now, because I just flipped that third bit by XORing with the 8. And then we can set it right back by XORing it again to flip the bit back. And it'll be 15 again, which is fun. A fun parlor trick, but it is useful. You'll get a lot of use out of XOR in CSCI 45. it's used for addition, in fact. Bitwise left shift and right shift are fun. There are these two arrows. So this is where these operators actually came from Bitwise thing. So like cout, we just overloaded it, but really it came from Bitwise operations. So it's always a number and then a positive number, or sorry, a non-negative number. It could be 0 through any other positive number, 0, 1, and onward. And what it does is it shifts away some bits. So like x left shift 2, if this is x, like 1, 0, 0, 0, left shift 2, it becomes 1, 0, 0, 0, like it adds some extra zeros here. And if there are other things over here, like 0, 0, 0, 0, it gets rid of those, because it's got to make room for two new ones on this side. That's what left shift does, and right shift does the opposite. Right shift that by 2, it becomes, well, it gets rid of those bits, and it brings in some new ones over here. It just becomes 1, 0 in that case. That's right shifting by 2 and left shifting by 2. Hopefully that makes sense. The one time that this gets a little weird is right shifting. It usually brings in zeros on the left side, but if it was a negative number, if this was an int and not an unsigned int, it will bring in ones instead. That's just a quirk of things. It's because the most significant bit, like the leftmost bit in a negative number, is 1, and so it thinks that it needs to bring in a new 1. It's useful, and so this is good for like getting which bit you want to set. Like I want to, instead of doing all this, like, hey, is the third bit set? You can just be like, oh, I don't know what 8 should be. You don't have to like come up with 8 yourself. And just like, you can just be like 1 shift left by 3. That'll set 1 in the third bit. I hope that makes sense. So you don't have to come up with like, okay, I need 8. I need 16. No, just start with 1 and shift by how many you need. And so that'll test if the third bit is set. Sets the third bit and the third bit only. And then another thing that the shifts are good for is multiplying and dividing by powers of 2. Like, what does it mean to add a 0? That's essentially multiplying by 2 to the 2. Yeah, 2 to the 2. And this is essentially dividing by 2 to the 2. Yeah. Get rid of the rightmost bits, divide by 4. Yeah. So a lot of cool stuff you can do with bitwise operations. I do not have much time to talk about them, unfortunately. Now, let's move on to RAII, which is a very odd little word. It is an acronym for Resource Acquisition is Initialization, which probably makes it even more confusing. So we'll just call it RAII. And the big idea behind it is that we've actually been doing this already. Don't worry. You've been doing it secretly. It's the way that we use classes in C++ to do fancy things. So the idea is that we represent a resource as an object, so something that we can own. We package it inside of an object. And the constructor, it goes and acquires that resource, and the destructor goes and releases it. And usually you don't want it to throw exceptions in that destructor for some reasons. And so somebody much smarter than me packaged up the idea of RAII and defined it in these words. It's when you bind the life cycle of a resource, one that needs to be acquired before use, like maybe heap memory, for example, or vectors, files, disk space, database stuff, anything that exists in limited supply, they say. So we need to acquire that before we do anything to it, and we bind that to the lifetime of an object. So when the object goes away, then we can deallocate the resource. Okay, we can unacquire, release the resource. All right, we'll talk about moving, that lets you transfer ownership of resources. That's a new cool concept that we haven't learned yet. And some things that you do know, at least to start with, strings and vectors. Those are using a RAII to allocate space for what it needs. Like it's keeping track of heap memory, it allocates them on construction, and maybe some addition operations, and then the destructor it goes and releases all the memory. Okay, so it acquired it, it got rid of it. And then smart pointers are a new cool thing that we'll talk about as well. Probably not this lecture, but the next one. Okay, so that is the definition of RAII. And now let's give some examples. So the first one is closing files automatically using RAII. So we have, remember, the IF stream to do this, to package up in C++ how to read a file. We can say, hey, please open that file in the constructor, like that. And the files will be closed automatically. Actually, you don't ever have to say ifs.close if you don't want to, because it will be closed for you when the object goes out of scope. So maybe there's a function that exists between some braces. Once you get to the closing brace, all of your local variables get released. Which means that their destructors get called. And the destructor of an IF stream closes the file, which is super nice. So usually when you hit a closing brace, that means that your object is going out of scope, and that is when the destructor will hit and get rid of the resource. So the game is you acquire the file in the constructor, that's what it's doing, and then you release the file resource in the destructor. Okay, that's the key for RAII in files, inside of files. So let's make a sample file, foo.txt. Be like, I don't know, hi, mom, blah. That's my file. And I will include fstream. And so the idea is inside of like maybe a function like void do file stuff, I can make an IF stream that reads from that file that I just made, and then I can do stuff with the file, like ... maybe like I do like ifs.get to get a character to read a little bit, and then the file will be automatically closed right here. Because IFS is about to go out of scope, as one says. Okay, so the destructor is going to get called, which will close the file, and nothing ever goes wrong. So I can say, do file stuff, please. There it goes. And we can say now that, and there's no output, so there's no errors. It just all works. It all works. And then we can do the same thing for exceptions. Like in the face of exceptions, even, files will get closed automatically because C++ calls destructors of stack variables as it tries to go and figure out which exception handler needs to be used. Oops. So do file stuff 2 will be automatically closed by C++'s exception handling mechanism. And that's if I throw an exception. And so even though I can throw an exception, yeah, I'm very confused as to why this is like not happy. Oh well. But do file stuff 2, please. This will throw an exception, but it will successfully like unwind the stack. So, and it will close the file still. Sadly, it fails right now, but I can try it and catch that exception. And like handle it. And it will just close the file for me because of RAII. It cleans up after itself, even in the face of exceptions. Gosh, is that wonderful. Then my last final example is timing a block of code. This is a really cute example of RAII. It's using it in a bit of a different way. So we can make a timer class, and what it'll do is the constructor will record the starting time, and then the destructor will get the current time and like figure out the time elapsed. Okay? And so we can use RAII to just time things, which is so cool. Let me show you this. Timer.cpp. So I can say, no, I don't even need anything. Oh yeah, I do. So I need, let's see here. I need ctime. That's what I need. And so I can make a timer class, which will save the starting time. And the constructor will set that starting time. And then the destructor will figure out the ending time. And get the difference. Which you have to static cast to a double for no good reason, because they're using a bunch of integral values. I want to figure out whatever this error means. Divided by clocks per sec. There we go. And then we can see out like time lapsed. Diff, and then it's seconds. Maybe a new line. And so the reason this is so cool and cute is it's an example of RAII, and that we can do the following. We can make void function to time. So I want to time the execution of this function. I want to know how long it took for this one function to execute. And I can simply do this. I can make a timer and then do the function, do the rest of the function. Okay? It'd be like, I don't know, int sum equals 0 for int I equals 0, I is less than a lot of ones and zeros, I plus plus, like sum plus equals I. And I can time this function. So because of RAII, the timer class will be destructed right here. Because I started the timer at the start of the function, now when it calls its destructor, the destructor is going to give me the time elapsed. I hope that makes sense. Isn't that fun? So just, all I have to do to time this one function is just declare a timer. RAII handles the rest. So I can say function to time. Oh no. And there we go. And it's just going to run by making a timer, starting its clock, and then once it's done, it like calculates the ending time. And suddenly, just by virtue of making this one timer, that's all I needed to do to time this function. Isn't that cute? Oops, this wasn't files. So that's how much time was elapsed. Maybe if I add another 0, this will suddenly work. Whee! It'll take 10 times as long, right? So yeah, we got 1.888 seconds now, and that is super nice. It's all working now. Okay, so that is RAII, and now let me set the scene for the next thing. So smart pointers, and they live in a new header file that exists from C++11 onwards. If you see these little tiny icons over here. No, I clicked the wrong one. It's called memory. Well, technically it existed before, but all the new stuff that we're about to talk about is all brand new. So smart pointers are pointers that are handled for you. Like it's heap memory handled for you. in a smart way, I guess. So that's the slogan, and let's talk about it a little bit. So just to set the scene for, I think I'm going to have to stop the lecture so that we can do the rest. We're running out of time a little bit, but smart pointers are brand new. So in this class, we've kind of been programming like it's the early 2000s. And that is okay because we need to understand how to manage our own memory. But really, almost nobody, unless they're doing very low-level things, actually uses new and delete anymore directly. Can you believe that? So this new concept, this thing called smart pointers, it handles new and delete for us. Okay, it keeps track of heap stuff for us. So they're under the hood doing new and delete for us, so that we don't have to care about, okay, I'm done with this now, let's please delete it. Okay, so maybe I can start with unique pointer, and we can go from there. So what you need to do is always include memory now. That's the new header that we're about to talk about. Unique pointer is a special class. It's a templated class, and it holds a T object. So a unique pointer of T wraps around a T object on the heap. So you can kind of think of it as like unique pointer of int. That's essentially equivalent to int star, which was initialized somehow by saying new int somewhere. Okay? If that all makes sense. It might be fuzzy, I understand. But that's essentially what unique pointer is giving you. It is access to an int if you dereference it. Okay, it's still a pointer. It's just like a weird type for that pointer. Okay, so think of it as a pointer to an int. It's just special in a certain way. Unique pointers are unique. So they make sure that only one copy of the object ever exists. And this is useful sometimes when you're like, okay, I don't want to share this with anybody. I need to make sure that only I am touching this memory right now. Okay? So they make sure that only one copy of the object ever exists. And you know how they do it? They get rid of the copy constructor, which is hilarious. It's beautiful. Let me show you. So let me show you unique pointer. And can I see anything here about that? Yeah, here's constructor. The copy constructor is deleted, if you see this. The copy constructor is deleted. So you cannot try and assign a unique pointer to somebody else. So you can't try and use the copy construction. I'm going to show you an example in a second. So yeah, what you do instead of calling new is you say make unique. It's a function for you. You make a unique of a certain T type, and then you give a value to the constructor. So if it's a primitive value, just give the value. Otherwise, you give the constructor parameters in between those braces to create a new unique pointer to a brand new thing of type T on the heap. So no new necessary. It does it for you. All right. So let me just show you a little bit about it. We're going to include memory. And then we'll be like unique pointer int equals, no, sorry, maybe IP or something, equals make unique 42 perhaps. Okay? So that is the idea there. Dun, dun, dun. And it is not happy for some reason. How in the world is it unhappy? Dun dun dun. Oh, sorry, it's because I have to give the template parameter here as well. Excuse me. There we go. And so normally people just use auto because you're already using it over here. So most people just write auto here. That's okay. We're going to spell it out. And so that just made us a new pointer on the heap. And my example is this made it for you, no new necessary. So it made it on the heap for you. So somewhere deep down, it's like IP, somewhere inside of it, it really does have a pointer onto the heap. It's got that 42. It's got it somewhere, somehow. And the idea is you only get one of these. It is unique. So its copy constructor doesn't exist, so you can't do the following. Okay? Which is super nice. It just makes sure that you only ever have one pointer pointing to this place. All right, and here we go. Are you ready? We can say unique pointer of an int IP2. Well, let's just copy that from IP. Surely I can do that. The answer is no, I cannot. Aha! Use of deleted function, copy constructor. No, we cannot do that. So they didn't let you use it. So you cannot do it like this. This won't work. So that gives an error. And there's a way to move it around. Like, you can only have it in one place, but you can move it around. We'll talk about that later. But that is a unique pointer in a nutshell. What you can do with it is you can get the value inside. You can use the star on it, just like a normal pointer. It's got the operator star overridden. Same with if it were a class, you can use the arrow as well. So that is the idea. And let's see here. We'll play around with it a bit right now. So I can say cout star IP to get what's there, just like a normal pointer. Okay. And then, oops, let's keep it there. And get back the 42. One thing you can do is, let's see what it, like, what's the default? What's the constructor for a unique pointer? What does it do? Because normally, if we were just to say, like, int star IP2, it would just make a random thing. But this one's a bit fancier. Like, let's see out IP2. Is this a thing? It's not quite a thing, but we can do the following. We can say get to secretly get the pointer that's inside of it, and then we can print that. So you should never be doing this, but I'm showing it to you for a reason. The default is sane. The default thing is null. That's super nice. Okay, and normally, IP's memory will be deleted automatically at the end of its scope, which means the closing brace of main for this example. So right here is where IP is going to get deleted automatically. That's super nice. But if you ever wanted to delete it earlier for one reason or another, you can use some of these operations. You can say it's either release or reset. One of them you should never do. And I think, yeah, release is ownership of the pointer, which means the pointer still exists. It's now your job to fix it. And it replaces it with delete. Reset is the one that you want to use now. Okay? So you can use star. As usual. And if for some reason you ever wanted to delete it early, you say reset. Okay, that's what you do. And you can alternatively give it something to reset it into, but normally you just call it without any parameters. And what it does is it destroys the object, and it if you give it something, it'll take ownership of that thing. but we can just say it like this to just get rid of the object. You can say IP dot release, and something that's really nice is what's IP now? What's it pointing to, really? It gets set to null. It gets set to null once you do this so that it doesn't accidentally delete it twice. It's all so beautiful and it's sane and it's like nothing is going wrong finally. It's pointers that make sense, okay? You can still run into errors, of course. You can still say star IP2 when it's set to null. So you can still shoot yourself in the foot, but it's still a bunch more cleaner, okay? It's just a breath of fresh air in the C++ world. So you can't do that. You can still segfault if you don't know what you're doing, but unique pointers are super nice. They make sure that you have only one copy to this place on the heap, and you can create a unique pointer by saying make unique. Okay? So that is all I want to say for this lecture, and I will see you in the next one where we talk about the other kinds of shared pointers, or the other types of smart pointers. So I will see you then.